Hello. In this lecture, we're going to do stochastic gradient descent. Stochastic gradient descent is the fundamental workhorse in deep learning generally. And I'm going to present various issues in stochastic gradient descent and various forms of stochastic gradient descent. In particular, momentum and something called atom. So I'll start by defining the simplest form of gradient descent. This is called Vanilla SGD, Vanilla Stochastic Gradient Descent. So the first step in the simplest form is to estimate the gradient by taking an average over the batch of the gradient of the loss on that batch element. So this is an expectation over drawing, say, XY pairs, say an image and a label from a batch, a mini batch, a set of those, of the gradient on the parameters for that image and that label, the gradient of the loss. And then we update the parameters by taking the parameter value and subtracting a learning rate times this estimate of the gradient. And this learning rate is incredibly important, and it's going to change over time. So I'm subscripting it with time. The learning rate is changing over time. So the change of the learning rate over time is called the learning rate schedule. And in this picture, we're seeing a learning rate schedule that was used quite a long time ago. It's not really used anymore, where the learning rate is being reduced by a factor of 2 in 2 steps. And the important thing to observe here is that for each learning rate, the loss reaches a stable value, a plateau, an asymptotic loss value. And that asymptotic loss value gets smaller as the learning rate gets smaller. So in the early phase of stochastic gradient descent, a larger learning rate makes the progress go faster. So in the beginning, you want a larger learning rate to reduce the loss faster. But that learning rate will eventually, if you just hold it constant, it will eventually reach an asymptotic, a plateau, which is too high. You want to get the learning rate to go lower. So you reduce the learning rate over time, and this is called the learning rate schedule. Now, there's another idea I want to emphasize, and this is temperature. So I'm simply going to define temperature to be the loss value that you reach at a particular learning rate. So for every learning rate, there's a loss value, and this loss value will go lower as the learning rate is reduced. Now, I also want to emphasize this general notion of hyperparameter. So this learning rate schedule is something that you design as part of the SGD algorithm. So that is a hyperparameter. The learning rate is a hyperparameter. I also want to think of the batch size as another thing that you can vary. It's sort of like a hyperparameter, but you typically don't tune it. You typically make the batch as large as your hardware will support. But still, I want to think of it as another parameter, because if you get more hardware, you're going to change the batch size. And we have to be aware of how changing things like batch sizes influences temperature and the appropriate learning rate schedule. And I'm going to argue, or I'm just going to assert, really, that what you really care about is the temperature schedule, the rate at which this asymptotic value that you reach is changing. So temperature is important in understanding how to control the performance of SGD, and in particular, how to control the search over hyperparameters. So temperature, I'm just going to take to be the asymptotic value reached at a given learning rate, the asymptotic loss. But eventually, in later lectures, I'm going to derive a formal relationship between this naive notion of temperature as the asymptotic loss value and actual physical temperature. So I just want to say a little bit about actual physical temperature. So physical temperature is related to, or even defined in terms of, a probability distribution over the energy of the state of a physical system. So a physical system, like a glass of water, has all these energy levels that it can be in, depending on how fast the atoms are moving. Each energy level has a certain level of motion of the particles. And the probability that it's in a given energy state is governed by Boltzmann's or Gibbs, this Gibbs distribution. Sometimes it's called Boltzmann, sometimes it's called Gibbs. I'll try to call it Gibbs. So this says the probability of a state is proportional to an exponential in its energy. So if the energy goes up, the probability goes down. And there's a constant involved in this exponential, which is the temperature. So there's Boltzmann constant times the temperature. You take the energy, you divide by kT, and that gives you an exponential that the probability is proportional to. So this is like a softmax. You're defining a probability distribution over state by normalizing an exponential quantity. And this normalization constant in physics, in statistical mechanics, is called the partition function. And in a later lecture, I'm actually going to derive a relationship between the Gibbs distribution and the probability distribution over model parameters. So what's going to happen is, as you decrease the learning rate, as you decrease the temperature, at any fixed temperature, you reach this asymptote, which is defining a probability distribution, a stochastic distribution over the model parameters. And that distribution under special conditions is a kind of Gibbs distribution, and the learning rate is acting like temperature. And as you make it colder, it's going to reach lower energy, and we're associating energy with loss. So the Gibbs distribution is often written, instead of 1 over kT, here we had 1 over kT is the constant in this exponent. Physicists and deep learning people write this with a temperature parameter beta, which is equal to 1 over kT. And it's the inverse temperature parameter. And it's always confusing, it's very confusing, because small beta corresponds to being hot, and large beta corresponds to being cold, right? Because it's this inverse relationship. So that's just confusing. But this is called the temperature parameter, and it's often used in any kind of softmax. This is a kind of softmax conversion from an energy to a probability distribution, and it's fundamental to statistical mechanics. Softmax is somehow fundamental to statistical mechanics and physical temperature. Okay, let's talk about the simplest form of SGD, this vanilla SGD. So this vanilla SGD involves two quantities. It involves, or two numbers. It involves the learning rate, and it involves the batch size. And here I'm going to just consider a constant learning rate, because what I'm really interested in is what's the temperature determined by the learning rate and the batch size. And in vanilla SGD, parameterized this way, these equations actually define the meaning of the learning rate and the batch size. It turns out that the temperature depends on both the learning rate and the batch size. When you change the batch size, you'll change the temperature, even if holding the learning rate constant. So the temperature becomes a function of both of these parameters. And that's not good. The reason that's not good is if what really matters is the temperature schedule, and you're trying to tune hyperparameters, if both of them affect temperature, changing one of them, either of them, will affect your performance. So it gets very confusing. You would rather be in a situation where you can directly control temperature, the temperature schedule, and understand you're controlling the temperature schedule and not get confused about what parameters are affecting that temperature schedule and how. So here I'm going to make an argument that tries to decouple the batch size from the learning rate. And we're going to try to make the temperature schedule dependent on a different parameter. We're going to parameterize it differently. So under this new parameterization, we're going to have the temperature schedule depend on only one of the parameters. And then it makes it easier to tune because you can directly control with one parameter the temperature schedule. So the way I want to derive this is to think about batch size 1. Okay, so I'm going to do a batch size 1 analysis and then relate that to a batch size B run. How is a batch size 1 related to batch size B for large batch size? So here's a batch size 1 update. And this is going to be the learning rate we use for batch size 1. I'm going to call that eta 0. That's the learning rate for batch size 1. And I'm going to look at the model parameters. So this is the equation governing the model parameters at time t plus 1. We're just using the batch size 1, so we're just minus eta 0 times the gradient at that time. The gradient of the loss at that time. Now, that loss is determined by the time and by the particular choice of the XY pair and the model parameters theta t. Now still doing batch size 1, what happens after capital B updates? Well, after capital B updates, we've taken capital B parameter updates. And those capital B parameter updates can be written as a sum of those updates. So it's going to be the sum over little b equals 0 to b minus 1. This is the sum over the batch elements. And this is the update we took for a particular batch element. Right, that update is going to look at the gradient of the loss at t plus b. So we're getting a different xy pair. This is giving us a different xy pair for each batch element. But with batch size 1, we're also getting a different model parameter at each batch element, right? Because we're doing an update every single XY pair. So we're getting a different model parameter over those updates. But if the learning rate is small, the model is not changing very much. The model is relatively constant. So this is approximately equal to using the same model at every step, right? So we're essentially using the same model at every step over this batch size 1 B steps. So this is approximately equal to this expression, which is the sum of the updates. In Vanilla SGD, we don't use the sum of the updates. We use the average update. We use an expectation over the batch, which is an average batch. So we would use 1 over n times this sum, or 1 over the batch size, sorry. 1 over the batch size times this sum. That's the estimate g hat t used in Vanilla SGD is 1 over the batch size times this. Now I can make these equal if I make this 1 over the batch size times the sum, but then multiply by the batch size. So this update with batch size B is roughly the same as running at batch size 1. So this update is going to give us the same temperature as a function of eta 0, the temperature that this batch size 1 runs at some temperature. This is essentially the same thing, so this is going to run at the same temperature as batch size 1. So this now runs at a temperature determined by eta 0, independent of the batch size, right? So, so note that the update here we're using is b times eta 0. Now, there was a very famous paper, well, it was famous at the time, in 2017. They discovered that if I scaled the learning rate with the batch size, so take the Vanilla SGD learning rate to be the batch size times some base learning rate, then you can run at very large batches. And the reason this works at very large batches is simply because now you're using this, by making this your learning rate as a function of the batch size, you're maintaining the same temperature schedule independent of the batch size. And this was a big innovation back in 2017 because they realized they could run with very large batches and get training to run much faster. They would reduce a week of training to an hour of training by using these enormous batch sizes, but they had to use this modification of the learning rate schedule. Okay. So now what I'm going to do is talk about variations on the simplest form of SGD, more complex forms of SGD. And the first thing I'm going to do is talk about momentum. Momentum is introduces another hyperparameter into an SGD algorithm. And it's going to use in the update a sort of moving average of the gradient rather than the batch gradient. So in addition to having a batch size, I'm going to take an average, a moving average of the gradient over many batches and make that the gradient estimate I use in my update, in my parameter update. Now, before I go into momentum as an additional hyperparameter in deep learning, I want to go over moving averages, and I want to develop an intuition for moving averages. So the first thing I want to talk about, the simplest thing, is a rolling average. So consider an arbitrary sequence, and these moving averages are used all over the place in deep learning. So it's important to understand the general concept of a moving average. So to understand that the general concept, I'm going to think about a general sequence, x1, x2, could be anything. These could be vectors, they could be numbers. So the first thing I'm going to define is a rolling average. So this goes on forever. You know, it's a very long sequence. Think of it as going on forever. But I want to know the average over the most recent n. Okay, so I'm going to take that's called a rolling average. It's taking the most recent n of these values and averaging them. So this x bar sub t is an average of the most recent n. It's the sum of k equals 0 to n minus 1 of one of the recent values of x, xt minus k. The problem with the rolling average is it's awkward to compute. You have to remember all of those values such that I can take out the one that's oldest and add in the one that's newest. And that's awkward to compute. It also has this problem that it's sensitive to the stochastic size of the one I'm taking out rather than just the one I'm adding in. So rather than use a rolling average, people almost always use what's called an exponential moving average. And an exponential moving average, intuitively, you can think of as an approximation of the rolling average. It can also be parameterized in terms of n, the most recent n. But when you formulate the exponential moving average, you keep this sequence, x tilde t, which is the moving average, and you update it by first multiplying it by a number less than 1, which is 1 minus 1 over n, where n is intuitively the window that you're averaging, and adding 1 over n times xt. Okay, so this is an exponential moving average, an EMA. the exponential moving average multiplies itself by a number less than 1 and then adds in a number times the value being added in, where this forms a so-called convex combination. These two numbers sum to 1. And you want to think of this as being very similar to a rolling average with a window of size n. And I'm not going to derive this formula, but I want to emphasize this intuition that it's sort of equivalent to a rolling average at length n. So this is our exponential moving average update, right? This is defining this sequence as this moving average of the xt's. And I'm not going to derive this, but you can write a formula for this value by looking at how each element of the sequence influences the value. So I can take 1 over n times the sum over all the previous values of the effect of that previous value on the current value, which is decaying exponentially because you're always multiplying by this multiplier 1 minus 1 over n. So you get a sum over all the values of 1 minus 1 over n raised to the power of how long ago that value was. And so you can see that this thing is an average of the previous values, but it's this exponential weighting of the previous values, which exponentially decays over time. And furthermore, the infinite sum of these coefficients, you can use a standard formula to calculate the value of this infinite sum, is n. So this is precisely 1 over n times a weighting on all of these values that sums to n. The weightings sum to n, and you're dividing by n. So it's an average over n, if that makes sense. Now, there's a conventional formulation, a conventional way of parameterizing exponential moving averages, which is to use a beta parameter, different from a temperature parameter, a beta parameter instead of the n parameter. So exponential moving averages are typically written as defining this exponential moving average sequence as beta, as being multiplied by beta less than 1, and then adding 1 minus beta times the new value. And these two equations are the same. We can simply take beta equals 1 minus 1 over n. An advantage of this formulation is that we now think of beta as being any real number in the intervals 0 to 1. So this can be any convex combination, with beta being a real number. But intuitively, well, beta is typically taken in deep learning to be 0.9, 0.99, or 3/9. And these values of beta correspond to n being 10, 100, or 1,000, just by this correspondence. So when you see beta being 0.9, think that you're averaging over the most recent 10. When it's 0.99, it's the most recent 100. 3/9 is the most recent 1,000. So what is momentum? So far, this is just exponential moving averages in general. In momentum, we use an exponential moving average of the gradient in the SGD update. So what we're going to do is we have our gradient estimates, g hat, and we're going to take an exponential moving average of the g hats, right? And I can write it in terms of n, or I can write it in terms of beta. Here, n has to be greater than or equal to 1. Here, beta has to be in the interval 0, 1. But here, I could take n to be any real number greater than or equal to 1. So I get this sequence, which is a moving average of the gradient estimates. And then I take my update to be a learning rate times this moving average of my gradient estimates. And in yeah, okay, I'll go ahead to the next slide. So in exponential, I'm going to call this exponential moving average momentum, right? So EMA momentum is just taking this exponential moving average of the gradient and using that instead of the actual gradient estimate. But what happens in an EMA momentum is the effect of a given point on the model parameters. Eventually, that point gets added in, the exponential moving average gets modified by that point by 1 over n on the first time, and then by less each time after that. And it turns out that the effect of one training point on the model after that model has passed that training point by a significant distance is 1 over n times the sum of how much it contributed at each time, because it's contributing over many times, and its contribution ends up being 1. So the contribution of a given training point to the model parameters over that sequence ends up being as if I just put it all in at once with weight 1. And that means that the momentum parameter, this choice of n or beta, for an EMA momentum does not affect the temperature, because the temperature is just the effect of any given one point on the model ultimately. So in EMA momentum, the momentum parameter, this choice of n or beta, does not affect temperature. It's naturally independent. It naturally has no effect on temperature, which is a good thing, right? Because we want to control temperature. We don't want our hyperparameters messing with the temperature. Unfortunately, Vanilla SGD in PyTorch uses a different parameterization of momentum, something called heavy ball momentum. And heavy ball momentum is a parameterization in which the momentum parameter of heavy ball momentum changes the temperature. And that's not a good thing. So what is heavy ball momentum? This is heavy ball momentum. And I'll maybe try to explain why it's called heavy ball momentum. So the idea is we think of this, we're moving through parameter space, but we think of the parameter value as the position of a ball moving through space. And the ball is heavy, meaning it has momentum, it wants to keep going, but there's a force on the ball that causes it to turn or slow. And there's actually two forces. There's like a friction force, and there's an independent force, which is actually determined by the gradient. Okay. So we keep track of the velocity of the ball. The velocity of the ball is being slowed down by friction. So there's a number less than 1 here, which is the friction that the ball is experiencing. And then there's a force on the ball, which is a learning rate times the gradient estimate. So this is sort of naive heavy ball momentum. Now, the thing to note is that this is not a convex combination. In EMA momentum, it would look just like this, but this would be 1 minus mu. This would be beta, and that would be 1 minus beta. Now, I can rewrite this as a convex combination, but only if I take this eta and divide by 1 over mu. And I should have said, once we take this to be the velocity, then the update is proportional to the velocity. So there's this physical heavy ball intuition that causes us to write it this way, but there's an EMA momentum intuition that causes us to write it this way. And the EMA momentum, I just argued, makes the momentum parameter not affect temperature. So we can, looking at this, if we replace this learning rate by a base learning rate divided by 1 minus mu, then we're going to get a parameterization that makes temperature independent of the momentum parameter. So what we're going to do, what I'm going to propose, if you're going to be doing this in practice, is to reparameterize, if you're using PyTorch, Vanilla SGD, and you have to give it this parameter, what you want to do is define a base parameter, a learning rate 0. We've already argued that you want to take the learning rate 0 times the batch size to make the batch size not influence temperature. But you also want to multiply by 1 minus mu, where this is the heavy ball momentum parameter. And you want to take the, you want to define your learning rate in Vanilla SGD, take your learning rate by this formula in terms of this momentum parameter and this batch size. And if you take your learning rate to be this, you'll get a temperature that's now independent of batch size and your heavy ball momentum. Okay, one last subject, adaptive SGD with momentum. This is called ATOM. This is the dominant modern SGD algorithm. I'm calling it an SGD algorithm because it's still stochastic and it's still gradient descent. But sometimes people will say SGD to mean vanilla SGD, and they'll say ATOM to mean this modified version of stochastic gradient descent. ATOM introduces even more hyperparameters, and I won't go through the details, but I'll give you a suggestion for a saner set of hyperparameters that better control temperature. ATOM is derived from lecture slides that were written by Hinton. So that's interesting to me because, someday some of my lecture slides might be important. But anyway, it was never really published. It just appeared in lecture slides. And ATOM, both RMS-prop and ATOM are adaptive. Now, what does that mean, to be adaptive? It means that we're going to use different learning rates for different model parameters. Okay, so we're going to, each model parameter is going to have its own learning rate. And I'll write those equations in a minute. But it's worth noting that ATOM uses both RMS-prop and ATOM, which are very similar, almost the same idea, except for bias, it's exactly the same idea. But ATOM uses EMA momentum, whereas RMS-prop uses heavy ball momentum. And I've argued that heavy ball momentum makes hyperparameter tuning much more difficult, unless you do this adjustment to decouple the hyperparameters. And that, I'm conjecturing that that's a main reason that ATOM is highly preferred to RMS-prop, simply because RMS-prop uses this EMA momentum, which makes hyperparameter tuning much easier. People will say it's much stabler, right? Less sensitive to the hyperparameters. Okay, so here's ATOM. So in ATOM, we're going to do 2 EMAs, exponential moving averages. This is the momentum, EMA momentum exponential moving average. This is an exponential moving average of the gradients. And I've written it here in terms of the beta parameters, because when you look at ATOM, you'll see the beta parameters if you read the documentation in PyTorch. So I've written it in terms of the beta parameters. So it's an exponential moving average of the gradient estimate, right? So ATOM is going to use this exponential moving average of the gradient estimate. It's an EMA momentum, not a heavy ball momentum. Now it's also going to use an EMA estimate of the square of the gradient. Okay, so this is measuring, it's not quite a variance, it's called a second moment. It's measuring, it's taking a moving average of the square of the gradient. Okay, so at each time point, actually for each batch, we get a gradient estimate at that batch And we're going to keep an exponential moving average of the square of that. And then this update has this interesting form. We're going to update the parameters by subtracting a learning rate times our EMA moving average of the gradient divided by the square root of our moving average estimate of the second moment. Okay, so the important thing to note here is that this is for a particular parameter. I'm not updating the parameter vector as a whole here. I'm updating each component, each particular parameter, each component of the parameter vector. I'm updating each component by adjusting the gradient on that particular component by dividing by the square root of the second moment. Now, why do I take the second moment? It's because I want to be insensitive to the sign. I want negative and positive gradients to both contribute to the sort of size, scale of the gradient. So if I take the square root of the second moment, I get something that's proportional to the scale of the gradient. So if this gradient is getting huge, both positive and negative, right? It's just big. I want to normalize it to make it sort of unit scale. So we can think of this gradient adjustment as a kind of gradient normalization. It's making sure that for each component, the scale of the update of that component is order the learning rate, right? We make this order 1. I'm ignoring epsilon. Epsilon is needed because this second moment might be too small, might be 0. And you don't want to, if this is 0, then this gets blown up inappropriately. But I'm ignoring epsilon for now. So this is gradient normalization. Just like you have value normalization going forward, you can think of Adam as gradient normalization. Okay, there's one more component of Adam, and I'm not really sure how important this is, but it's a standard difference between Adam and RMS prop, is that it's called bias correction. So what is this about? Consider an exponential moving average. I want an average of over something of size of length n, right? By analogy with rolling averages. Now in an exponential moving average, you typically initialize your exponential moving average to be 0. Now when you initialize it to be 0, these updates are only changing it by a little bit every tick, every time step, because you want an average over the last n, and we're initializing our average over n to be 0. So it's going to take a time scale on the order of n to overcome that initial 0. So for n steps, I'm estimating the gradient as being way too small. So Adam fixes that. They call it bias correction. And I'm going to give my own form of bias correction, which is doing pretty much exactly the same effect as what Adam actually does, but it's a little simpler to understand. Suppose we wanted the exact average of the first t, right? So suppose t is less than n. We want we're at the beginning, so t is like 5. It's way too small. Suppose I just wanted the estimate of the first 5. Well, I can do a running average estimate where the convex combination is designed such that this xt is always the exact average of the first t. And that's what this does. It takes t minus 1 over t times the previous plus 1 over t times this, and that ends up giving you the exact average over the first t. And you can write it this way, 1 minus 1 over t plus 1 over t times this. So it is a convex combination. This is a convex combination, and it's keeping track of exactly the first t. Now, eventually, you want to switch to your rolling average. You don't want the average over all time. You want the average over the last n. So you can do that with this equation. As t gets large compared to n, you switch this to 1 over n. It's a simple idea. You keep an exact average of the first t up until you reach n, and then you switch to a moving average with a time constant of n. So here's that atom with bias correction. And this is essentially the final form of PyTorch atom. Now, atom has issues with hyperparameter tuning. I mean, it's claimed to be very stable, but you can make it more stable by thinking about temperature, right? You really want your temperature, you really want to control your temperature schedule, and you want a single parameter that controls temperature. So I'm not going to derive this, but here is an adjustment to atom, to PyTorch atom, which will make it more stable, which will make it less sensitive to the parameters other than temperature. It's going to focus temperature into one parameter, and all of the other parameters are going to be designed not to influence temperature. So we do this by introducing these other independent parameters. So these are the independent parameters, the hyperparameters of atom. We've got an EMA average parameter, a window size, NG, for the momentum. We've got a window size for estimating the second moment average. We've got this epsilon, and it turns out that epsilon is an important hyperparameter of atom. And we've got atom's learning rate. So the claim is, if I redefine the parameterization, take different independent parameters, I'm going to talk about NG0, NS0, the batch size, epsilon 0, and eta 0. And I'm going to redefine what you feed into atom in terms of these other independent parameters, a reparameterization. And the claim is, if you use this reparameterization, then you're going to get an algorithm whose temperature depends just on eta 0, or is largely determined by eta 0, the temperature schedule. So you're focusing the control and temperature in one parameter, and the other parameters don't affect temperature. This particular way of defining atom's epsilon also has the nice feature that if you take your independent parameter epsilon to infinity, then atom smoothly and gracefully converges to vanilla SGD, which is a good thing, because sometimes vanilla SGD is non-adaptive. Vanilla SGD actually does as well as atom. And if you can smoothly move between being adaptive and being non-adaptive, there can be a point on that smooth transition that's optimal. But in order to smoothly move to vanilla SGD, you want a parameter that controls that independent of the other parameters. And so this reparameterization does that. Okay, so we've covered various versions of SGD, and I focused on temperature, batch size, momentum, and atom. I did not cover the classical convergence theorem. That I took out at the last moment, forgot to delete it from the last slide. It's just a classical theorem that you don't really need to know. I've tried to keep the slides on just what you need to know. So I want to thank everyone, and I'll see you next time.